All right, everyone. Welcome to, I guess, week 2 of February. Um, this is actually, I think this will be my second to last session teaching everyone. So, yeah, I hope everyone has had a good experience with these lessons. And let me know if you have any feedback. Let me know. Um, yeah, I hope everyone has taken something out of these. So, um, yeah, so this week is going to be statistics and probability. Next week we'll have off because of Spirit Week. And then the last week of February will be our last week where I'll go over geometry. So this week we'll be talking about chapter 15 and 16, statistics and probability. Um, there's a whole field of, there's a whole major that you can have in college dedicated to statistics. So um, yeah, if any of this starts to interest you, definitely continue learning more in college. We're going to do the very basic stuff that you probably have some familiarity with, which is mean, median, mode, range. And then the probability will also be the more basic things, which will just be what you'll need for the competitions anyways. Um, but yeah, I think some of this material is definitely the most um, practical and applicable. I use some of these principles in my job, so um, definitely good to get a good idea of these things. So let's get started. So we will not be doing the set game this week, and we probably won't for the last one either, unfortunately, just because there's so much material to cram. But um, instead, we'll be doing a fun problem at the beginning. This is going to be a bit of a large problem, but it'll be the only one I'll have you everyone do. So here's the problem. So example one, given a set here, as you can see, let A be the mean, let B be the median, C be the mode, D be the range. Find the mean of the set A, B, C, D. So when you have your answers, please send it to me incrementally. So if you have A, send that to me, B, etc., C, D. Yeah, this is a big problem. So
How do you calculate the median again?
Could you say that again?
How do you calculate the median?
Yeah, so the median is going to be the middle number. So one of the best ways is to just maybe sort the numbers or look at from lowest to greatest.
Wait, so if it's 1, 3, and 4, then the median is 3.
Yes.
Okay.
You might see though that it's a little trickier this time. Sorry, I've just muted my computer, my work computer. Okay, we'll be going over in 1 minute. Mm. All right. So I think, yeah, let's start going over this. So, um, right. So for this problem, I think one of the best things to start with is to just write out the list in ascending order as a sorted list. And the reason why is it's a lot easier to see the median in this case, right? So um, the median, as I was explaining before, is kind of the middle number if you sort everything from least to greatest. And the issue is that in this group of numbers, there's 10, right? So if it was just 1, 3, 4, the median would be 3. Well, in this case, um, the there's no one middle number. So I'll tell you what we do with that. But for mean, what we do first, because I want to just go A, B, C, D. For mean, we add up all the numbers and then we divide by the total number of numbers, which is 10 in this case. So we'll get that A is 34. So for the median B, what we have to do is we have to look at the middle two numbers, which is 22 and 34 in this case. And we actually just take the mean of those two numbers or the average of those two numbers. And that becomes our median. So that's just one random thing that you just have to know if you want to calculate the median. So in this case, the average between 22 and 34 is 28. So that makes B 28. Then for mode, that just means which number appears the most frequently. If there are multiple numbers that do this, usually we say that there are multiple modes then. But in this case, there's only one number that appears twice and everything else just appears once. So the mode in this case is 34. So C is 34. And then the range is just the biggest number minus the smallest number. And if you look at a sorted list, you can see that 90 is the biggest in this case, negative 10 is the smallest. So the range will be 100. Each of these numbers kind of give a different sense of the um, points, the numbers that we have here. So these numbers kind of describe the numbers we have. So the average is kind of 34. Another way of looking at average could also be kind of 28. Um, this kind of says what appears most frequently. In this case, it's 34. Then the range is just saying how wide of a range of numbers do we have, right? So that's kind of the reasoning why we have all these terms. Um, so now the question is just to find the mean of the set A, B, C, D. So we have A, B, and C, and D. So we just do like the same thing. We take the average of A, B, and C, and D. So we add them up, divide by 4 because there are 4 numbers. And from that we get 49. Does this make sense to everyone? Thumbs up, thumbs down, thumbs kind of sideways. Yeah, so a lot of this stuff is just anything that's on the math competition is just going to be knowing what these terms mean. And for the next part of this, what I wanted to do is give you a cool fact about mean, median, mode, range, because um, this is actually used right in real real life. And it might be like, why is this useful? And it's more useful actually when we talk about graphs, or we're talking about distributions, is a better way of saying it. And what I mean by graphs are like these kinds of graphs. Um, Anyone want to volunteer what kind of a graph this is called? What kind of a way of plotting numbers this is called? Any volunteers? Kaden?
Is it the stem and leaf?
Yes, this is called the stem and leaf plot. And the way you read it is this is kind of the base or the stem, and then these are the leaves. So this is saying that there's a 20 in this plot. So there's 20 here, then there's 30, just like how we had a whole list of numbers. One of the numbers is 20, another number is 30, another number is 32, another number is 35. There's two 41s, right? So this is kind of, um, so the mean, median, mode, and range are very useful when we have like more than just 10 numbers, but maybe hundreds, maybe millions. Um, and when we have these graphs. So another graph is this. Anyone know? Actually, it says it right there. So this is a histogram. So histograms are basically ways of bucketing your different numbers. And these numbers usually will represent, say, people, right? So maybe you have, I didn't count how many people there are here, but however many people there are here. And they all have like approximately these weights. Um, then if you have, instead of like saying the whole list of numbers, you say, how often are people this weight or that weight, the frequency, then you get what I'll call is a distribution here, right? So you maybe have seen like the bell curve or the normal distribution. Um, the height of it corresponds to frequency, and um, the x-axis are just the different values. So that's kind of what this histogram is also doing here. So you get an idea of how frequent are things. So when you have these kinds of graphs, the cool fact that I wanted to share is here. So since this y value is frequency, and the x values are the different numbers that you have, the height of the distribution, the part where it's the highest, is actually going to correspond with your mode. So if you go down to the number, that'll be your mode here, right? Um, the median will make the area of both sides 50-50. And then the mean is going to be such that if you put your whole distribution on like, this fulcrum, it's going to be balanced. So there's an equal number of weight on the left and the right. So that's why these two are actually a bit different. They're both kind of a sense of the middle, but they're a bit different. So this is kind of what mean, median, mode, range is, still the same, but this is what mean, median, mode become when you go into more complicated statistics. So that's just something I wanted to share with that. And now let's go into probability. So this can sometimes be related to the different statistics stuff that we talk about, because sometimes this distribution is a probability curve. Anyways, let's go into probability practice. Here is the first problem. Please send me in private chat your answer for this. I'll give everyone about a minute or so for this. All right, so let's start going over this. So for this problem, the big parts of probability is to figure out how many possibilities are you interested in versus how many total possibilities are there. So in this case, there are 14 equally likely marbles that we can take, right? So there's 7, give me a second, this thing I have here. All right, give me a second. Yeah, so there's 7 orange, there's 5 green, and there are 2 blue marbles. And the total number of marbles that we're thinking about drawing is 7 because it's asking what's the probability of drawing an orange marble, right? So there are 7 marbles that would be, oh, orange, versus the 14 total marbles that there are in there. So because of that, the probability would be 7 over 14 because yeah, there's 7 choices of orange out of the 14. So that's kind of what that's what probability means. And if you simplify this, you get 1/2 or 50%. So that is this problem. So yeah, generally what probability means is how many are you interested in, and then what is the total amount. And the big thing to make sure is that whatever you're counting, make sure that they're all equal probability. Okay, here's the next question.
It's six-sided die, right?
Yes, good question. So it is a 6-sided die with values 1, 2, 3, 4, 5, 6. And for all the problems, because I'll have a few more dice problems, for all the problems, they're all 6-sided dice. Give another minute for this. All right, so let's start going over this problem. So the probability for the first die is 2 out of 6 because it's saying less than 3, and notice that it says less than 3. If it ever says less than or equal to, then it includes 3. If it just says less than, it doesn't include 3. So your only options are 1 and 2 for the ones you're interested in out of 6 total values. For the second die, it will be exactly 1 out of 6 since there's only one number greater than 5, which is 6, and then 5, 4, 3, 2, 1 are all not, so 1 out of 6. And something to generally remember is when you see the and of two events, that means multiply. So you see the 2 out of 6 and 1 out of 6, these two probabilities, you and them together, and that's a multiply. So the total probability is 2 6 times 1 6, or 2 out of 36 chance. And that is also simplified 1 out of 18. I do also want to show you why we multiply the numbers. Generally, multiply means and the reason why is because you can start like from the beginning, and when you make that first dice roll, right, there's it's either going to be less than 3 or greater than or equal to 3. Those are the only two options. And you'll see that 2 out of the 6 options will get you into the less than 3 universe. And then 4 out of 6 options will get you into the greater than or equal to 3 universe, right? So you could have rolled a 1, a 2, 3, 4, 5, 6. And those are all so there's a 2-6 chance you'll be less than 3, 4-6 chance you'll be greater than or equal to 3. If you ever have heard of parallel universes, I think if you think about probability in terms of parallel universes, it actually helps a lot with figuring out probabilities. So in one universe, less than 3, it's 2-6 probability of that happening, greater than or equal to 3, 4-6 probability of that happening. And now, in each of these universes, you're also going to roll a second die. And as a result, there's a 1/6 chance of getting greater than 5, but also a 5/6 chance of getting less than or equal to 5. And when you want to calculate the probability of getting from the start to the final result, you go through the probability of getting to that universe, right? So you can start here, get there's a 2/6 chance of getting here and then 1/6 chance of getting here. So the total chance of getting to this universe where you have a less than 3 on the first and greater than 5 on the second is 2 out of 36. The probability that you'll get, say, less than 3 on the first dice, but greater than or equal to 5 on the second would be 10 out of 36, etc. Does this graph make sense? Thumbs up, thumbs down, thumbs in the middle. Okay, cool. Yeah, so you can kind of think of it like again, back to the parallel universe theory. Every time you do something, it's going to split the universe into different probabilities of what will happen. And that's kind of what's happening every time you introduce another random event. So, and then some of these worlds are more likely than others because there's more possibilities of this happening than the other. So yeah, so in our case, this question is saying less than 3 for the first die, greater than 5 for the second die. We'll see that this is probably 2 over 36. What about this question? One die is rolled, what is the probability that the result is less than 3 or the result is greater than 5? Give another minute for this. All right, let's go over this one. So in this case, there's only one die and it's an OR. So we can get the same probabilities. Less than 3, it's 2/6. Greater than 5 is 1/6. And generally, if you see OR, that means add, add the two probabilities. So in this case, 2/6 plus 1/6 is 3/6 or 1/2. So if we're looking from that parallel universe way that I was showing before, you roll your dice, and this time there's actually 3 different buckets that you could fall in. You could be in the less than 3, greater than 5, or between 3 and 5 inclusive. So there's a 2/6 chance of getting here, 1/6 chance of getting to the greater than 5, and then 3/6 chance of in this middle, right? And when we're saying or, um, we want to add the probabilities that we're interested in, which is either less than 3 or greater than 5. So that is these two possibilities here. And by adding that, we get 3/6. So what about this question? This is our last probability question. This one's a tough one. All right, I'm gonna give another minute or so and then we'll go over this. This one's definitely a challenging problem. If anyone has any questions, if this is unclear, let me know. This is basically saying, so I'm gonna roll one dice, roll another dice. If the first one's less than 3, or if the second one is greater than 5, either one, if both, that's fine. Only one of them, fine. Only one of those conditions is satisfied. Then that is like, that's gonna be the good, that's what we're interested in. So what's the probability that when we roll the dice, we're gonna be like, great, the first dice is less than 3 or the second dice is greater than 5. All right, let's start going over this. So for this problem, it's very deceiving. So we do what we were doing before. Probability of first dice, first die less than 3 is 2/6. Probability of second die being greater than 5 is 1/6. And oh, when you see or, that means add, right? So 2/6 plus 1/6 is 3/6, right? Not exactly in this case. What you want to do instead is you want to add first die less than 3, 5, 2, 6. But then you also want to add instead the probability of the second die being greater than 5 and the first die not being less than 3. I'll explain more why, but this is what we need to do in this case. So that would be 2/6 plus, so we got that 1/6, and then there's a 4/6 possibility of the first roll not being less than 3. And if we calculate this out, you get, so multiplying fraction. The first one you can make into 12 out of 36, and then you multiply fractions, add them together, 4/9. So here's why. Here's why we do this kind of convoluted step. So if we go back to our parallel universe idea, right? What we're really looking for here, so for the probability of the first die being less than 3, that's this part, right? So this whole first branch is going to encapsulate the die being less than 3. As long as in the first die roll we get less than 3, this is satisfied. And you'll see that if you add up the probabilities at the end, 2 out of 36 plus 10 out of 36, that gives you 12 out of 36, which is also just 1/3. So that makes sense. 1/3 probability less than 3. Cool. The second clause here, second die greater than 5, is these two universes here. So as long as the second die is rolled to 5, like greater than 5, then we're good. So it's either greater than 5 here or greater than 5 here. Again, this should add up to 1/6 because there's only 1 out of 6 possibilities for that. So 2 out of 36 plus 4 out of 36. That's 1 out of 6. Cool. When we're looking for or, we're saying that either the first die worked or the second die worked. So that's this. The purple here is actually going to be both, right? So in this very first case here, the first die is less than 3 and the second die is greater than 5, right? So there's a 2 out of 36 possibility that's happening, but nevertheless, that's the case there. This blue one here is strictly falling in this, oh, well, at least the first die was less than 3. This possibility here is, well, at least the second die is greater than 5. in this case, right, we're looking at the probability of all of these. So you want to add actually all of these probabilities together, right? Um, and what happens when you add first and second by itself, 2, 6 plus 1, 6, is that you overcount this purple line here, right? So this purple line here, you double count because you counted it for 2 out of 6, and you also counted it for this 1/6 here, right? So that's why when you say that it's them added together, 3, 6, you're actually overcounting by 2 out of 36. Now, if you look at this, right? If we look at this new way of reading this, we add the first die less than 3. So that's both of these branches, right? So that's going to be, we add this, the top part, and second die greater than 5 and first die not less than 3. So that's specifically this branch here, the bottom red branch here. So really, all we're asking is we want to add all 3 of these probabilities and just not this probability. And that's why this works, because you're adding all of this first event, and then if the first event doesn't succeed, but then your second event succeeds. So that's why the formula is like this. Something I also want to teach you, and this you might not have realized also, but you can do something called complementary counting. So you can basically look at the complete opposite, right? Probability that the first die is greater than or equal to 3, and the second die is less than or equal to 5. And then you can do 1 minus this total opposite of what you're looking for. So in this case, if we're looking for the probability of first die greater than or equal to 3 and second die less than or equal to 5, that's this. That's 20 out of 36. And if we get the opposite probability, that's 16 out of 36, or 4/9. What this looks like on this graph is we're specifically finding the probability of this last path that we do not want, right? This is what we are not looking for. This is the branch that we're saying, this is not, like, if this were to happen, we'd be like, oh no, it wasn't less than 3, and the second die wasn't greater than 5 either. This is the only case we're worried about. So what we could do instead of doing that formula we did before is just say 1 minus this last probability, this last possibility, and that gets us the same result. Does this make sense?